Hi everyone. Today I'm going to have the presentation for the efficient enumeration of distance hereditary graphs and Ptolemaic graphs. And this is a co-work with Kazuaki, Yamazaki, and Ryuhei, Uehara. And here we first give the outline for today's presentation. We know that in the research field of graph algorithms, there are some algorithms which achieve high efficiency by restricting input graph class. And from this viewpoint of the developer of such algorithms, graph catalogs are always useful because we can use it to do our test data and for the unit test of an algorithm under our development. So algorithms that enumerate the elements in a certain graph class are investigated in recent years. However, the algorithm they used are strongly depend on the target graph class. In recent years, a more general framework for graph enumeration based on the reverse search technique is investigated. And here is the general framework for the enumeration algorithm. They use reverse search as the main technique of the general framework for enumeration. And in reverse search, we assume that the elements of the target set have some adjacency. And reverse search makes DFS or BFS managed search in such a structure without management of the information about whether each element has been visited. So that since we define a parent-child relationships, we define a unique relationship in the target set. And we construct a unique family tree of the spanning tree, then the traversal of family tree corresponding to the enumeration. And the data structure we're going to use in our algorithm is called DH tree. The DH tree is a tree structure which represents a distance hereditary graph. For a distance hereditary graph, a DH tree can be uniquely generated by some specific rules. And DH tree also corresponding to unique distance hereditary graph. So it is easy to understand that we can figure the isomorphism problem of distance hereditary graphs by solving the isomorphism problem of DH tree by a rooted, labeled, or partially ordered tree. So now let's start with our first graph classes today, which is called the distance hereditary graph. And here we first give the definitions of the distance hereditary graphs. A graph G is distance hereditary if it is connected and every induced path is isometric. That is, if the distance function in every induced subgraph of G is the same as in G itself. And here we give a simple example for distance hereditary graphs. Though it is quite difficult to understand based on this definition, there is also another definition, which is based on the generation rules of distance hereditary graphs, which is a graph G is distance hereditary if it can be constructed from a single vertex by the following operations. The first is add an appended vertex, which is a new vertex that is adjacent to precisely one existing vertex of the graph. And second is called strong twins, which is for an existing vertex X, we add a new vertex Y with close neighbors, with the same close neighbors. And here close neighbors means all the neighbors that adjacent with the vertex X, which include vertex X itself. And the third one is weak twins, which is for an existing vertex X, we add a new vertex Y with the same open neighbors. And open neighbors is also all the vertices which adjacent with vertex X, but without vertex X itself. So we can understand the generation rules based on the graphs. And here for the pendant case and strong twins, we add a new vertex with the same close neighbors. And for weak twins, we add a new vertex with same open neighbors. And now we can give our enumeration algorithm for distance hereditary graphs. Here we use K1, which is a graph with only one vertex, for the root of the family tree, since K1 is the simplest distance hereditary graphs. And we use removing a vertex operation by the reverse of generating operations. So the parent of each distance hereditary graph should be determined uniquely, and we can select one vertex from multiple possibilities of this vertex. Vertex can be a vertex that created at last. And here we give the pseudocode for the enumeration algorithm. We start from K1, and each time we set a graph, we choose a graph from the set. We choose a graph from set S, and every time we find all the possible graphs that can be obtained by applying the generation rules based on the three kinds of rules we mentioned before. And then we check the parents of the new generated graph. If it is same as graph G, then we put it back into the set S until all the elements we want are generated. And then we can give our theorem first, which is that distance hereditary graphs with at most n vertices can be enumerated in big O n to the power of 3 times for each. And for the second part, we are going to introduce the Ptolemaic graphs. And in mathematical areas, there's a theorem called the Ptolemy inequality, which shows that for any 4 points A, B, C, and D in Euclidean geometry, the following inequality holds. And we use the inequality in a graph, and we get the definition of the Ptolemaic graphs, which is a graph is Ptolemaic if any 4 vertices u, v, w, and x in the same connected component satisfy the Ptolemy inequality. And here we also give a simple example for Ptolemaic graphs. And now we give the relationships between 3 kinds of graphs. Here we know that the Ptolemaic graphs is the intersection part of distance hereditary graphs and chordal graphs, which is already been proved. And distance hereditary graphs we already introduced right now. And the chordal graphs, which is also a famous graph class in graph theory. So now we know that Ptolemaic graphs is a subset of the distance hereditary graphs. And based on that, we can consider that the Ptolemaic graphs may have the similar generation rules for with distance hereditary graphs, which is graph G is Ptolemaic graph if and only if it can be constructed from a single vertex by the following 3 operations. Here we know that the 3 kinds of operations are same as distance hereditary graphs, with only one different. That is, when we create the weak twin of the Ptolemaic graphs, we have to make sure that the vertex should be simplicial vertex. And here, simplicial vertex means that all the open neighbors of this vertex X can form a clique. And based on the generation rules and use the same framework, we can give the enumeration algorithm of Ptolemaic graphs immediately. And on the left side, we have the same framework. And more precisely, when we generate the set CH, we first need to compute if all the vertices in a Ptolemaic graph is simplicial or not. And then when we create the weak twins, we first check if the vertex here is simplicial or not. If it is, then we create weak twins. In this algorithm, the 2 steps are marked as red color is bottlenecks of this algorithm. Both 2 steps cost big O n to the power of 3 times complexity. So to improve the time complexity of this algorithm, we introduce the following concept, which is called the simplicial function. And here, we define simplicial function as follows. And the input of this function is a vertex, and a vertex from Ptolemaic graph, and the output is true or false. So if the vertex if the vertex v is simplicial, then we output true. Otherwise, we output false. And now we consider how the simplicial function update, since we do the generations of the Ptolemaic graphs. First, for the pendant case, whatever the vertex u is simplicial or not, when we add a new pendant on it, and it becomes false, since the new pendant did not adjacent with all the original neighbors. But and of course, the new pendant should be true, since there's only one neighbors of this pendant. But the pendant have a special case. Let's consider that when we generate a new pendant on K1, then we get K2. But now both K1 and K2 are simplicial, since both two vertices have only one neighbors. And second one, for the strong twins, we have, if we create the strong twins of a vertex, whatever is true or false, and it didn't change, and the new strong twin should be equal to the here we have the example. The S should have the same value as U, since both of them share the same close neighbors. And for weak twins, we know that both two weak twins share the same open neighbors, so the simplicial function should also be equal. But only difference is that for all the neighbors of U, open neighbors of U or V, we call a vertex W here. And for all the vertex W, we have the value of SW becomes false, since we know that two weak twins are not adjacent. And for three kinds of generation rules, we know that for pendant and strong twins, we need big O n one time to update. And for weak twins, we need big O one time to update. And for weak twins, we need big O n time to update. So we have the lemma 3 now. That is, for each generation rules in theorem 2, the update of the simplicial function S can be done in big O n time. Since we have n vertices for total, so big O n squared time for a given DH tree, where n is the number of the vertices. Now we consider, now we back to the generation rules for Ptolemaic graphs. Since we use the simplicial function, and for the first bottlenecks of our algorithm, we can update into the following steps. That is, we can update simplicial function by DH tree, which costs only big O n square time, so that we improved one of the bottlenecks of this algorithm. And of course, for Ptolemaic graphs, we have that Ptolemaic graphs with at most n vertices can also be enumerated in big O n 3 time for each. And for conclusion part, first we give the distance hereditary graphs with at most n vertices, and we can enumerate them in big O n 3 time for each. And by using the same framework for Ptolemaic graphs, we also can enumerate them in big O n 3 time for each. And now we know that both two kinds of graph classes all can be enumerated in big O n to the power of 3 time. And we also implemented the algorithm of distance hereditary graphs and the simple algorithm of Ptolemaic graphs, and ran them on the supercomputer. And the results are provided on the website. And for the future work, we consider the enumeration algorithm for distance hereditary graphs and Ptolemaic graphs based on DH tree. since we know DH tree and distance hereditary graphs are not one-to-one mapping, and DH trees, one distance hereditary graphs may have several DH trees representations. So we have to figure the isomorphic of the DH tree first, then we may do our enumeration based on DH trees, which is maybe much more faster than the algorithm we use now. And that's all for today's presentation. Thank you for your listening.